So now moving on, so the last thing that I want to talk about is adjusting the Bohr model. Because as it turns out, the Bohr model works really well for hydrogen. But that's it. If you try to apply the Bohr model to anything else, helium, lithium, sodium, etc., it fails. And the reason why it fails is because hydrogen only has one single electron. And this is where this is going to get crazy. This is where there's like a mind explosion. So we talked about interference with light. Okay? So we talked about how, like, if I have two interfering waves, right? Let's say if they destructively interfere like so, and I add these together, then I've got nothing, right? Or if I add them together constructively, then it results in an even brighter spot. Well, this is where this gets crazy. Electrons in atoms also have wave-particle duality. Sorry, that's getting sloppy. So, once again, electrons in atoms, and this is the crazy part of quantum mechanics. As soon as you remove an electron from an atom and send it off into vacuum, it behaves like a particle. So a free electron, so we'll say that again, free electron is like a particle. But a bound electron, acts like a wave. That's crazy. So light isn't the only thing that's suspect to wave-particle duality. So, and what I mean by bound electron is an electron that's in an atom, an electron that is bound to a nucleus through those electrostatic negative-positive charges. Okay. So now the reason why the Bohr model works for hydrogen is because there's only one single electron. There's nothing for that electron to interfere with. However, if let's say we put two electrons in here, so I'm going to populate, let's say, this level with two electrons, okay? Well, as soon as I put two electrons in that same orbit, they actually start interfering with each other. They can interfere with each other constructively, or they can interfere with each other destructively. All right? And that makes the Bohr model just not work. We can come up with other models that get quite complicated, and that's largely what quantum mechanics is all about, is trying to calculate these types of properties for more complicated molecules. However, the gist of it, to adjust the Bohr model, now instead of having these orbits, like these planetary orbits, these orbits actually have a wave pattern, right? And so you can see here n is equal to 1. It's really hard to tell, but n is equal to 1 would only have one oscillating period, okay? N is equal to 2 would have two oscillating periods. N is equal to 3, this one's easier to see. N is equal to 3 would have 3 oscillating periods. I don't even know if I could draw n is equal to 4, but you get the idea. These orbits are no longer like these planetary orbits, but they themselves are also like waves. And the waves of these orbits are given to us by the de Broglie wavelength equation. Okay? And in the de Broglie wavelength equation, we still have Planck's constant h. Okay? But now this becomes mass of the object in question, and this becomes the velocity of the object in question. Now, in this discussion, we've been talking about electrons. And if we were to use the de Broglie wavelength equation, we would use the mass of an electron, and we'd have to know what its velocity is. And that would actually give us the apparent wavelength, so the distance, you know, from peak to peak, or the distance from trough to trough, right? That would give us the apparent wavelength of an electron. However, de Broglie, he was a really smart quantum mechanicist, a very young one at that too, when he came up with this, very young man. He said, well, electrons, because they have mass, if those are suspect to wave-particle duality, then so too must everything else that has mass. So a human, a proton, a tree, a car, whatever. If an electron can have wave-particle duality, so too can everything else. And this is like, this gets into big picture stuff, and it actually starts to get into general and special relativity, when now we start talking about if I accelerate an object to close to the speed of light, so like a human or a tree or a car or something, right? If I accelerate myself at or near the speed of light, you would start observing my wave properties. So I largely exist as a particle right now, right? Like I can, just like a particle can collide with stuff and bounce off something, like my head is like a giant particle colliding with a metal pole. I definitely bounced off that. I did not interfere with it and like pass right through it, okay? Like an X-ray can pass right through your body. But according to all of this, and this is yet to be proven, but according to all of this, if I can accelerate myself to at or near the speed of light, so that would be the velocity approaching the speed of light, then I would start to have wave properties. I could interfere with something. I could maybe even pass right through something if my wavelength was sufficiently small enough, okay? And this is what's created the basis in science fiction shows for, you know, beam me up, Scotty, right? That's the whole idea, is that if you could turn a human into a wave, then you could make that happen, okay? And so here's one final picture of this whole idea of these wave-like orbits. So this is hard to imagine this, but if you look at this here, this n is equal to 3, and this is called stable, and what that means is when I'm following this wave, let's see if I can draw it, there's just a continuation. So round and round it goes. You don't know where it stops. You don't know where it finishes. So I get 3 complete waves round and round, okay? And so that means these numbers, these principal quantum numbers n, they have to be whole numbers. Because now, right, if I make it 2 1/4 or whatever, it's not going to start and stop at the same place. Another really good example, you know, for you guitar players or string instrument players, you actually can observe this all the time when you like pluck a string. So let's say you're plucking the strings right here, and the bridge is located right here. Well, this becomes some length, okay? And so now if you get exactly 1/2 wave occurring over this, that would be the principal quantum number. So that would be the principal tone of the instrument. Okay, and if you started chopping this in half, and the way that I could chop that in half, think about this, string instrument players. I would put my finger, so let's, right? If I put my finger at exactly that fret, I would have found the first harmonic of the instrument. Maybe you know that term. On guitar, that sounds like that really high-pitched bing. When you make that sound, bing. When you do it exactly half of the length of the guitar, that's the first harmonic. If you were to do it 1/4 of the length, it would be the second harmonic. If you do it 1/8, it would be the third harmonic. This also creates the basis of octaves in music when you split these waves up based on whole integer number wavelengths. So there's some pretty cool stuff that's going on here. But the important thing to note is you can't have these integer numbers. It's got to be these whole number wavelengths. Okay, folks? So this stuff is pretty tough to grapple. It's out there. It's very abstract. We have very little things in our common everyday experiences that allows us to kind of think about this stuff other than like music and instruments. So it's pretty weird stuff. So if you're left thinking, whoa, that's weird, it is. It's very cool though. So I would encourage you to find some like Nova channel or BBC or Discovery Channel stuff on quantum mechanics, and particularly on de Broglie wavelength and wave particle duality. There's some really out there wacky stuff that's physically correct, but it's just wacky. It's different and bizarre. It defies your everyday experiences. Okay, folks, so that's all I'll say now. So just these 3 videos for this week. Next week, it'll be maybe 3, possibly 4 more videos. So this should be enough to get you through the first part of homework, part 1. So that's a 20-pointer. So after you finish all 3 of these videos, do yourself a favor, do me a favor, just finish that part 1 homework. All right, folks. Later, Hosen.